Good evening, colleagues, dear colleagues. Good evening, dear friends. I'm surprised I know many of you. Even though I'm here 10,000 kilometers from home, South Africa is my second home. So thank you also to Grant and to WITS for hosting me here. It's been a wonderful day, and I hope I'll lead it to a suitable conclusion. Title of my talk is the Geological Framework and the first results from ICDP BASE drilling in the Moodies Group, 3.22 billion years old, Barberton Greenstone Belt, South Africa. And as you see from the author line in the lower left, it's not only me standing here, okay? There's also Prof Nick, with whom I interacted in this drilling program on an almost daily basis, calling each other on the phone, checking off items of interest, of need, the finances, the drilling, the staffing, the next visit, and so on. We interacted daily, and he will be sorely missed. I'm also standing here to represent the BASE on-site geoscience team, and I'm here to represent my co-proponents on that ICDP proposal. So I'm standing in, and I'm standing on the shoulder of giants. I already threw two abbreviations at your head. BASE stands for Barberton Archean Surface Environments, and ICDP, as you heard from Louise, stands for International Continental Scientific Drilling Program. The talk here will be structured in a fairly simple manner. You can read faster than I can talk, so there's no need to read this to you, and I'll get started with introduction and fundamentals. The whole thing started in 2016 with a research proposal which was funded, that is to hold a research workshop, a field workshop outside Barberton to talk about drilling research boreholes. And the members and the attendees of that drilling workshop formed then the BASE science team. There were about 70 of us. We gave ourselves a structure. We visited candidate drilling sections, and we discussed the pros and cons of the various proposals, the various sections I had sent my colleagues to at night. And some of you were in the audience, and you may even recognize yourself 10 years, nearly 10 years younger. This year are my colleagues from the Science Management Board. I tried to select them by country because they were expected to write proposals to get co-funding after we had obtained seed funding from ICDP. And lastly, this year is the BASE on-site geoscience team. At least two of these 11 people are today in the audience. One is myself, but the more important person here is Pumi, who is standing in the back here, to the right, holding a camera, waving at us. Pumi, shown here in the front right. Pumi was our EOP, Education, Outreach, and Publicity Officer, with her golden tongue and her excellent communication skills. What will this talk be about? I'll field a large question at you. It is, are we alone? I'm not going to answer this question with a yes and a no. No, sorry, don't wait for that. However, I would like to give you a couple of thoughts along that question. It's a question that has been around certainly for thousands and thousands of years, as our ancestors gazed upon the sky at night and wondered whether any of the stars up there represented, the twinkling stars, I should say, represented messages or signs of life. And certainly we are spending large amounts of money for exploring other planets here in our solar systems for the signs of fossil or for perhaps even extant life on Mars, which was a planet fairly similar to Earth 3.5 billion years ago. Secondly, we don't even just know the 8 or 9 planets in our own solar system. If you look here at the web page, currently, as of last week, we know of 5,573 confirmed exoplanets. and several hundred additional candidates. And this page is updated, I think, weekly. So we are studying these exoplanets not so much to find life, but rather to assess the parameters of habitability. We know the orbits, we know the sizes, we know their periods. Sometimes we know a bit about their atmospheres or their temperatures. And we are trying to come up with statistical measures whether life on any of those would even be possible, life as we know it, carbon-based and water-dependent. And lastly, our question addresses a bit whether life as it is something that forms easily under a range of circumstances and under a broad range of environments, and therefore should be common on other planets, and we should not be alone, or quite the contrary, that we might find out life only forms under the most extraordinary and positive and benevolent circumstances that happen to have occurred here on Earth, and therefore we might be alone in the universe. So much for a rather philosophical introduction to a drilling talk. Have you heard of that before? Right. We know of one planet where life has formed. It's not far away. Easy to study. We don't have to travel through space. We could go back to the roots of our own planet and look at rocks that are familiar to many of you. Banded chert of the Onverwacht group, banded iron formations of the Fig Tree group, microbial mats in the sandstones of the Moodies group. We need to go back to the very oldest rocks of our own planet. Okay? However, we don't know very much about our own planet in its baby stage. We know very little about whether there were continents, how many, how large, how they were shaped, what topography they had, whether they were hard enough, firm enough to support mountain ranges. We know nothing about their coastlines. We know therefore little about global tides, nor the oceans, composition of the oceans, temperature of the oceans, ocean currents. Because we don't know about the ocean, we know little about the atmosphere, except that we are currently on our third atmosphere. We know the atmosphere was rich in CO2 and in nitrogen. It may have been dusty. It may have contained methane or ammonia. We know little about the Earth's spin, but it was probably twice as fast as today. The day had only about 12.5 hours in the Paleoarchean. The moon was at about 67 to 71% of its present distance, and therefore the tidal forcing, not the tides, but the forces exerted on the water particles in the oceans were about 3 times as high as they are today. Therefore, we should expect hypertidal regimes. Unfortunately, we don't see those. We don't know why. Because we know so little about the consequences of rapidly spinning planets, we know little about the climate, the number of Hartley cells. We know therefore, we don't know the weather. We don't know whether it was windy or not. Because we know little about the climate and precipitation and humidity and temperature of the atmosphere, we know little about weathering, the dominance or the absence or paucity of chemical weathering, even though there are many indications of an intensive chemical weathering regime. Intensity of the solar radiation in the visible light was probably at 70%, more or less like it is in this room here, a constant dawn or dusk atmosphere, but the UV part of that radiation was much higher, and we would have gotten a sunburn within a few seconds rather than within 20 minutes. We had abundant volcanism, but we know little about the sources and what fed them. Meteorite impacts peppered the early Earth, but we know little about their rates and the consequences for life. It may have benefited life, it may have destroyed life. And most of all, and most interesting to us of all, is whether in that set of how and where, in that set of apparently adverse circumstances, life could form. Okay? This is how we imagine the Archean to have looked like, and many of you are familiar with this very influential painting that is in the Smithsonian Institution in Washington, D.C., and is from '85, I have my doubts. Yeah? I wonder about various aspects. And the Archean may have looked differently. Yeah? So nowadays, we don't do oil paintings anymore, but we ask artificial intelligence. And some of you may have fun creating ancient landscape of your own liking as you follow the imagination of your own favorite geological countryside. So this is what I imagine the Archean to have looked like, and don't think that this may be correct. This may be all wrong, but these images are just hypotheses, okay? This is how it could have been, how our current data sets would allow us to see the Earth as it may have been. However, we don't really know. Yeah? You see, for example, that the AI has a limited data set when it comes to shorelines. It has only few shorelines without seagulls. Okay? And I'm looking forward to the first geology-trained large language model, yeah, that can distinguish between shield volcanoes and stratovolcanoes, or that knows what a microbial mat is, and so on. So this is just for introduction. Yeah. Now, where on earth do we go to look for that old record? You here should all know that. Sorry, I just turned this off. We are here in South Africa, and we're looking at greenstone belts. I'll explain in a second what greenstone belts are to the students in the audience. And you see here a couple of the locations I held presentations. I wasn't in Cape Town, I was nearby in Stellenbosch, but I was in Bloemfontein. I'm now up here in Gauteng, and I'll be in Durban and in Nelspruit. The greenstone belts are these little green things, but if you take away the sedimentary cover, you see that they actually should be far more widespread. They may be actually underneath us, and we simply don't know. If I switch over to a geological map in which Carl here was involved, and Tinos was involved here too. I don't know Gunter Brandl, whether he's here or not. And you see, here are the greenstone belts we know, but underneath us maybe many, many more. And these are our records, stratigraphic records of early life. Among them is the Barberton Greenstone Belt. It's the largest and the prettiest and the best preserved. And therefore, it serves to bring up another map of Carl, 1983, showing the essential makeup of stratigraphic makeup of the Greenstone Belt. Onverwacht Group in blue and green, Fig Tree Group in the middle, and the Moodies Group, subject of tonight's talk, in yellow on top. The stratigraphic column of the Greenstone Belt is astonishing. We are talking about 10 to 12 kilometers or so of the Onverwacht Group, which probably is an anorogenic volcanic plateau surrounded by oceanic environments, and consisting of basaltic and ultramafic rocks overlain by something that until shortly before was called subduction related, and I replaced it by orogenic because I doubt whether plate tectonics existed at that time or subduction existed. So that's the Fig Tree Group with a lot of greybackies and banded iron formation, conglomerates, dacites, shales, and that in turn is overlain by the Moodies Group about up to 3.5 kilometers or so of mainly terrestrial and shallow marine, quartz-rich sandstones, conglomerates, and some shales and banded iron formations. Look to the right at that massive time span brought up by that impressive 15 or 16 kilometer thick stratigraphic record. It's covering 350 million years of Earth history. Of course, with interruptions, okay? But there's much that we can learn from it. In cross-section, again, for those of you unfamiliar with greenstone belts, they are encased in the basement of our cratons, in the basement of our oldest continental nuclei between older coeval and younger plutons that are shown here in red and orange. And you see they are folded and the margins are highly metamorphosed in several ways. And nowadays, of course, as I have shown you on the example of the Carpwall craton, many of them are covered either by strata here to the left, these might represent Witwatersrand and Transvaal and so on, or by the strata you see to the right, which may represent the Mozambican coastal plains. Okay? The Barberton Greenstone Belt has another reason that we should study it closely, that is a rather unusual topography, because it sits intermediate between the Highveld, shown to the left. Yeah, where's the Highveld? Well, maybe up here, not quite yet, or down here, as you go beyond Bad Plas, and the Lowveld, which is visible up to the upper right towards Kruger National Park. The stratigraphic relief is 1,700 meters difference, and that is unusual for greenstone belts, which are typically low-lying because they're old and they have been away from plate boundaries for a long time, and they're typically in the center of continents, forming within continental nuclei. Now, this is different because it's at the margin of the Highveld. So here's the overlay, the topographic overlay. And time-wise, I'm going to take you back here on the time arrow that you see from the left, origin of the Earth to the presence. I'm going to take you back to that 350 million year interval, actually an even much smaller part of it, at the very beginning of the Archean, the so-called Paleoarchean, an extremely important part in the history of life on Earth. And you see how how Earth exchanges atmospheres and how different metabolisms come and go, and how Earth in its first half, and many of you are aware of that, was the bacteria planet. No eukaryotes existed. There are no cells with a nucleus or with an advanced metabolism. Photosynthesis existed probably, but it was a planet densely populated by a variety of bacteria. Yeah, bacteria that we largely do not see today anymore because they had to go into hiding due to the ambient conditions that we cherish and require so much. Let me lose a few words about the Moodies Group. It's ideal for early Earth studies. Everything you will see in the following field photographs are Moodies strata rocks. This is actually a view from Eswatini into South Africa. You see the strata trend across the national border. Everything is vertical and coming towards us. The stratigraphic thickness exposed here is certainly several kilometers. There are a couple of folds in here. Not everything is steep. This is what we call the soccer field. No one ever has played soccer here, but I have been there with many, many field trips. It's a plateau on hill number 2. Highest mountain in the back is Shokolwa, 1,903 meters. And it shows, but again, the strata are vertical and they're striking towards us. 3.5 kilometers of stratigraphic thickness exposed in the Eureka and in the Saddleback synclines. Outcrop area across virtually the entire Greenstone Belt of 40 by 110 kilometers. And then as you hike up Shokolwa, just beautiful, beautiful outcrops, ideal for measuring stratigraphic sections, but as you see, occasionally interrupted by these grassy patches, ridges separated by grassy fields. We more or less know what the depositional environments of the Moodies Group encompass. It's mostly terrestrial environments from alluvial over a lot of fluvial and coastal plains, shorelines and deltas and so on. This here is just a bit of shallow marine and a tiny bit of deep marine. And this here is a view of just a recent analog, difficult to find because most environments associated with water today are vegetated. Yeah, and those that are not are cold, but Moodies wasn't really a cold environment either. Moodies strata are tightly folded and often overturned. Very interesting structural mapping. And the tight folding was probably a result of a deformation phase we call D4 that is largely associated, but not only due to the uplift of the Onverwacht Andecline, which you see here in blue, the core, and the limbs in green of the Onverwacht Andecline. And Alex Hoffmann will already have recognized that the white line here is the Buckreef chert, one of the thickest Archean sedimentary chert units, up to 300 meters thick. and that unverwachte andecline plunges 90 degrees. Okay, it goes straight down into the ground. Sometimes it plunges 95 degrees. So just by simple geometrical reconstructions, you can, the most conservative size estimate of what the unverwachte andecline minimum field area must have been would be something 15 kilometers up in the air, 15 kilometers down, because the outcrop length of that white dashed line, the Buckreef chert, is 30 kilometers, which must have been the minimum diameter of this thing. But an amazing structure, and of its erosion, much of the Moodies was sourced, and we see that, most currents go towards the northeast. Conglomerates in the proximal positions turn into the widespread and well-known sandstones, which then turn into fine-grained sandstones and siltstones further to the northeast. And we also see it in the textural maturity of the sediments from immature boulder conglomerates and lahars going into coarse-grained, medium, fine-grained sandstones, and then some siltstones. Angularity, sorting, and grain size all increase. No, angularity decreases, of course, towards the northeast. Moodies is excellent because it has very little strain. So we see all kinds of sedimentary structures. And I'm not going to go through all these things here, but you may recognize the ripples here. You may recognize the faucets. You see the mud cracks. There are concretions. There are crystals growing in fine-grained tuffs. There are all kinds of things in here. And many of them are associated not only with physical or chemical processes, but biological processes, because there are quite a number of microbial mats, spaced at millimeter spacing and reaching up to 1,000-meter thickness. And they are not everywhere in the Greenstone Belt, but limited to one part of the central Greenstone Belt. But we think that they may be similar in many respects and may be identical to shallow marine and coastal modern cyanobacteria, which of course are photosynthesizers and which we see today commonplace in lagoons and bays and in low energy shorelines. A final, I think, special attitude of Moodies Group and why we go there to study early Earth history is that it provides a unique, very short, high-resolution magnification of early Earth time. And I'll illustrate that in that simple diagram. It plots the stratigraphic column, these 3.5 kilometers or so on the vertical axis, and on the horizontal axis, 30 million years of time, from 3235 to 3205. 30 million years of time, no less. And when you then plot the available age dates, all measured from tuffs that are interspersed with from the uranium-lead circumdating of tuffs that are interspersed with these sandstones, you see, there are a couple of shrimp dates that have very low analytical errors or analytical uncertainties, and the rather wide white lines are the LA ICP-MS dates, which have the analytical uncertainty of about 5 or 10 million years or so. So when you then try to put a line through all of these to satisfy the data requirements, you see that it would be possible to deposit all of Moodies in a geological instant. I say a geological instant because the analytical uncertainties at the base and at the top of the Moodies group overlap. Okay, we cannot tell the beginning and the end of the Moodies apart for sure. We kind of know and so on, and yes, you see this goes to the left, it becomes younger towards the top, but we require help, and therefore I'm really glad to have Clarissa and Scott and Nadia and a number of other people on our geochronology team to learn to tell Archean time. I'm coming closer to the drilling program. Set up, objectives, drilling design. Why do we need to drill? It's a commonplace problem. Moody strata are commonly weathered where they are continuous, and they are discontinuous where they are unweathered. Remember some of the outcrop slides I showed you just 5 minutes ago. Therefore, our principal objective was to recover unweathered and continuous sections. So we got together in 2017 for that workshop, and it was an intensive workshop because while we were out during the day, or sometimes only during the morning, in the afternoons and in the evenings, we formed committees and subgroups, and we defined the detailed research targets, the objectives for our proposal. I'm not going to read this to you. And by the way, anyone interested in this talk here, feel free to approach me after the lecture, and I'll pass you a PDF or so, or even the PowerPoint if you want to extract parts of this here. Happy to share all the data. But if you just glance over the orange headers, we were interested in the pro-delta phases, mostly because these were the lowest sedimentation rates. That is, this would be our highest resolution receptacle for, let's say, micrometeorites, anything raining down from the atmosphere. We were interested in cyclostratigraphy, for example, expressed in shale laminae. Of course, a lot of points here associated with these microbial mats that I just showed you. We call them crinklies, whether they were indeed photosynthesizers, whether there are any traces of oxygen left immediately above or below within nano or micrometer distance from these carrigenous mats, and so on. We were interested in the paleosoils, which at the surface are obviously difficult to differentiate from modern and recent soils. We were interested in global surface environments, such as the temperature of the oceans, of the atmosphere, the composition of the oceans, and so on, the redox potential, the pH value, and so on. And then we had secondary targets in paleomagnetism, in magmatism, basin dynamics, and geochronology. So in the end, we ended up with 8 boreholes, selected boreholes, and many of you are familiar with the terrain. Barberton is here. Yeah. This is the road in yellow, the road to Bad Plas, up here towards Nelsproyd, up here towards Kaapmuiden, and here the R40 wiggles across the mountains towards Eswatini. And so you see the uppermost, in the upper right borehole is located in the Eureka syncline, again Carl's map, and 1 in the Dicedale syncline, 4 in the Saddleback syncline, and 2 in the Salzburg syncline. These were the sections that we selected after our field inspections. If you do this, if you project these data on a more modern, slanted Google Earth view, we're looking here towards the northeast. You see K and P in the background, the Kruger National Park. Barberton is to the lower left. We are floating, hovering above Agnes Mine, essentially. You see base 4C, B, and A in the foreground. Number 3 is over here. There's the Lomati water tunnel going underneath Saddleback Hill. There's number 2, there's number 1. Number 5 is the 2 number 5, A and B would be to the lower left. We can correlate between all these boreholes using the low resolution stratigraphic logs from these different synclines that are separated by faults, because they have a really nice marker in the middle. The green unit, it's the Moodies lava, and from there on you go up and down. So our boreholes are these gray cylinders marked with these red numbered circles. And in addition, we scheduled, planned, and even executed the sampling of 3 tunnels. It's the Lomati water tunnel to the right, and the 2 light gray cylinders to the left. These are 2 adits of Agnes Mine. All 3 of them transect Moodies strata at right angles for considerable distances. Then we got our funding together. And you see that large baby blue funding comes from ICDP, covering about 65% or 60% or so of our drilling expenses. ICDP only funds drilling. There are no related research. But then with the funding from ICDP in hand, which was in early 2019, we turned around to our national funding agencies and said, please give us some seed money. This is how it works. And indeed, we were successful to obtain considerable funds from Germany, from the US, and South Africa. South Africa is a member in ICDP, and Japan, as well as smaller amounts from other countries. I should also say that stubborn, but in the end, unsuccessful efforts were made to obtain similar amounts of funding from the UK, from Australia, and from France. And the colleagues who did that and who went to three iterations, I think, in France and in the UK have to be applauded for their stubbornness. In the end, it turned out unsuccessful. We didn't know that when Nick Bukes and I decided to go ahead, and we hoped that we would be flush in cash, but in the end, it turned out we had to make do what we had at that time, and it still worked out well. Operations and outreach. Once we got started, we had 8 wonderful, interesting, diverse drill sites. You see them just field shots here and numbered. Some of them were in pine plantation, eucalyptus plantation, recently harvested, grassland, the end of a forest road in a pine plantation, a parking lot. Back there is the paved road, the R40, wonderful. And this was the hairpin turn of a steep mountain road within Fairview Mine in the Eureka syncline. So that was pretty tight, but we did it. And just moving these drill rigs, I'll show you, we used up to 3 simultaneously. Was always great fun. It took about 9 days from the end of drilling to start of the new hole, pulling the casing and logging and loading and moving and trammeling and unloading. Many of you are familiar with these neat little drill rigs. They are walked essentially to their drilling spot by someone with a joystick walking next to them. It's like a dog on a leash, but different. And this was our drilling schedule. We started in November 21, November 15th, perfectly in time for the start of the rainy season, as we had not wanted it to be, but it turned out that way. And then by February and March, there were 3 rigs active, and then for the rest of the season, 2 rigs, and we ended in late July after 9 months of drilling. The different colors represent the rigs and the sites. And our sites were always very compact, somewhere between 12 by 15 meters, fenced in with a bit of security fence back there, or these, no, it's not security fence. We had a firm fence only at site number 2 because it was highly accessible. We also had a guard there overnight, whereas the other sites were all hidden in the forest. No one would find them, and we could safely abandon them and leave them alone overnight. After drilling, we logged all boreholes with caliper and GR, gamma ray, magnetic susceptibility, and the very useful borehole resistivity imager that you see down here, as well as, of course, a direction analysis. Because most of the strata were vertical or subvertical, we had to drill sideways. And because you cannot drill horizontal, we had to drill at 45 degrees inclination, which was okay with the drillers. In addition to these 8 boreholes, as I had mentioned, we succeeded in sampling 3 tunnels. One of them is not a mining tunnel, it's a water tunnel. The Lumati water tunnel connects the Barberton Reservoir up in the mountains with a water purification plant in Reimers Creek, just outside the city limits, and is the principal water supply to Barberton and to adjacent Mjindini. And it runs underneath Saddleback Hill. Here has a length of 2,780 meters, goes through the Saddleback Fault and ends at the Barbrook Fault. And interestingly enough for us geologists, it penetrates 2 opposing limbs of the Saddleback syncline, each about 1,000 meters thick. Beauty at 90 degrees angle, okay? And in order to allow a sample there, we had to link up to the engineers for the annual inspection, which had not taken place for 10 or 15 years. And the engineers gave us 4 hours to sample 2,800 meters of section. So I drummed up support. Bertus, were you among us? I'm not sure, no, you weren't. Anyway, there were 9 geologists, so 3 teams of 3 each of them logging 700 meters or so. The first 500, 600 meters were spray coated with concrete. And after 4 hours, we actually came out with 100 samples. As you see here, because the engineers had drained the water only partially, we were chest to ankle high in water, which was great fun after a while. And we used a canoe to transport our samples. Yeah. And the other underground tunnels are more conventional. Here we are hovering again over Barberton. We're now looking towards the southwest. And Agnes Mine is in the foreground, the Greenstone Belt to the left. This is the frontal tectonic unit of the northernmost tectonic unit of the Greenstone Belt, Moodies Hills block. And we sampled the 22 level added, the surface trace of which you see here in red, and back here the Ben Lomond or the Princeton Tunnel of Agnes Mine. Here I overlay here the outline of Moodies Hills block. Again, strata coming at us subvertically, and each of them about 900 meters to 1,000 meters of section. Now, Bertus, that is you, up there, right? So again, 100 samples or so. We had the most perfect setup for core processing that you could imagine. It was a spacious, underused, or virtually unused industrial hall in downtown Barberton, the so-called Buyers Hall, Barberton Iron and Steel. In its left wing is housed the Barberton Regional Museum. In its right wing, a couple of coffee shops, and the center part was unused. We installed some shading and made our own compartment, used the front half as an exhibition space because we wanted to be very public, and the back space as our rock processing area. You see excellent light, concrete flooring, rafters, level, smooth, security, electricity, water, no air conditioning, but hey, you can live with that. We set this up in a systematic way. This here is a diagram showing essentially a map view of how we did this. Again, the left half, from here to the left, was our exhibition space for the public. And you will see that we had quite a handful of public to do. And then the other processing is the core processing was done to the right, and we set it up in a clockwise fashion in stations, and each station had a processing and a waiting area. The next photograph is taken here from that corner and goes towards the ox wagon. Looks like this. So you see the ox wagon here in the background. It was used as a movie prop. And here you see all of us at work. Pumi at the reception desk, Chris Rippon orienting core, Rod Tucker marking core, Dora Paprika splitting core. You see 2 trays in front of her, and Derek and Musa repairing the rock saw, even though the rock saw was excellent. Or maybe they're just changing the blade or doing something. And this is Ryan Tucker here, probably watching a YouTube movie. Now he's entering. Pumi, what was he doing? He was entering data into MDIS, that rather obtruse data management system that you have to use when you want to be financed by ICDP. And this year, of course, here is my chair and my workstation. I was doing the lithologic description. A particular aspect, one that makes us unique and attracts a lot of attention, was that we were drilling in a World Heritage Site. 7 of our 8 holes are within the Barberton-Maconchwa World Heritage Site, which was declared by geologists or on the advice of geologists in 2018 for its unique universal geologic value, and therefore became off-limit to any exploration by the expert South African mining companies. 4 years later, the foreigners move in and want to drill. In a former gold province, right? Agnes Mine, Fairview, Sheba, New Consort. It took a lot of convincing that we were not drilling for commercial reasons, that we were not drilling for gold, that is. People were very familiar with drilling, as they are in most places in South Africa. We were drilling for knowledge. Why would you do that? Right? We were drilling out of curiosity. And we overcame these suspicions first through these 4 points, which you see written on the right. First, I had been around for a long time, and I always make sure that I get an article in the Lohfelder or the Barberton Times when I'm there, and that I give a talk at the GSSA branch of the Barberton GSSA branch, that I'm just part of the furniture there. So I had an established track record. Then, thanks to Pumi back there, we played all the media that you can imagine at full volume, okay? All institutions, anywhere, anyone who would listen to us would get a mouthful from Pumi on what we were doing. Thirdly, we had an open door policy. Our gates, this big iron sliding gates at the buyer's hall, were always open. Anyone could walk in without notice, whether it was lost Dutch tourists, where are we, what's going on, all the way to 2 or 3 school buses filled with 100 screaming third graders, right? And then lastly, we promised the community that we would leave a legacy, something sustainable. So you see Rod giving tours here, explaining drill bits here at site number 2, which was our most public site. We had all these field trips for government, for industry, for academic institutions, for schools, and so on. That was great fun. It was also great to have them go again, so that we could do our work again. We flooded the internet with newsletters every 2 weeks, 1-page newsletters, messages of the day, image of the day, ICDP websites, and so on. This is logs. So we had a firm media presence. We had posters at the drill sites. Here to the left, it says taxpayer money at work. Yeah, this is your money. And we tried to be as visible as we could at all. Pumi, of course, was our star. She was on 50/50. She was at the radio station. She hauled us off to the radio stations once a week, Monday evenings, I think at 6. She fed our Facebook page. She handled the journalists. Okay, we even had a science article. Okay, not science research, but science news. But still, we were in there. So thanks again, Pumi. First results, what did we find? And well, we drilled 8 boreholes between 280 and 490 meters length, plus these samples from these 3 tunnels. And I'll quickly show you cross-sections through these 8 boreholes without saying really anything, except that the strat columns that are building up here always go from stratigraphic bottom to stratigraphic top, okay? So let me go back once. Actually, this had the surprising effect, maybe unfamiliar to many, that the further you drill, the younger the rocks get, okay? Because they are overturned. Not here, but here, yeah? And also in the next 3. And this is the right side up again. That's in the Stolzburg syncline. And we drilled, as you see here, through a thick section of jaspilites that were far thicker than we had anticipated. And that was a section we had to drill 2 boreholes because a single borehole would have gone over 500 meters length and therefore would have become expensive. Our rates went up at 500 meters. So now we have all these strat columns, and we can correlate even better. So here is Carl's stratigraphic shorthands for all these Moodies units. And we now can correlate using the first jaspilite, MDI1, the second jaspilite, MDI2, MDI3, the third, if it exists, is way up there. And you see a couple of quartzites in light gray. But you also see here the the tunnel sections. And you see how wonderful complementary they are to the boreholes, yeah? Because they were taken in regions and in the Moodies Hills block which had not been accessible for drilling for various reasons. So we are very, very glad to have this combined data set. Which rocks did we find? I'll show you 5 different rock types really quickly, okay? Because certainly we cannot come up with any solid science and nature paper, groundbreaking fundamental truths yet, whether we are alone or not. We found a lot of sandstones, different sandstones of interest, in particular, of course, to people interested in provenance and weathering and sedimentation mechanisms and surface environments, wind speed, current strength, water temperature, water viscosity, and so on. We found quite a bit of microbially laminated sandstone in at least 4 boreholes, not just one. And we found, in addition, some stromatolitic sandstones. We call them, that's an old term, by now we call them mini mounds. Bertus just notified me that he accepted our paper. No, it was another paper. That one, you accepted a different paper. This year already came out a few months ago in astrobiology. We are not sure what they are. They are little knobs about fingernail to stamp size, formerly laminated, conical, look like mini stromatolites, may have been biogenic, and may be tufa, yeah, travertine. And we're not quite sure, but you see them here, you see them here. So this is not kerogenous matter, not carbon crinklies like you see down here, but something different. We're not quite sure yet, but of course people are working on it. We found a number of what we tentatively might call one day paleosoils, and for the time being we're calling them VAZ, vadose alteration zones. Yeah, it's a zone, okay, and it's in the vadose, it's above the groundwater table, and it's altered. And where's the alteration? The alteration consists of these bands of coarse crystals. And if I enlarge this a bit, these are bedding parallel and are silicified gypsum concretions. Gypsum in the Archean, yeah, SO4, oxygen was rare, free oxygen was rare, therefore it was difficult to make molecules or minerals containing that much oxygen associated with a single sulfur atom. And, but yeah, we have good evidence that these may have been, that these once were gypsum concretions. At the moment, we are a bit clueless, even though I already published twice on this with my former postdoc Sami Napan. And first we thought they were evaporitic concretions and would indicate a semi-arid environment with groundwater rising and precipitating solutes. And now we are on a different tack, and perhaps more hypothetical, but also more interesting. You know about the Archean volcanism. So certainly a lot of SO2 came out, sulfur dioxide, along with that volcanism. And in the absence of a protective ozone screen, the SO2 at the upper end of the atmosphere is then disproportionated, taken apart by UV radiation, by energetic radiation into sulfur, which is a solid, a yellow solid, and sulfate. Yeah, you take 2 SO2 and you make S and SO4. And the sulfate is soluble in water and would rain down. Sulfate in the water combines with the hydrogen, it makes sulfuric acid. These here may be the results or the dried out residue from sulfuric acid rain. Think about what this would do to feldspar, yeah? Or to any rocks, virtually any rock on the surface. I'm speculating, yeah? Aside from the yellow rain, we might have had acidic rain as well. We'll find out. We found quite a number of conglomerates from alluvial and braided fluvial environments, presumably. And when you look at them more closely, you see that some of them are quite conventional, feldspar porphyries or dacites, some rhyolites, and a lot of chert varieties, most of them black, but also gray or banded, sometimes ferruginous. But then there are also conglomerates that consist of angular shale fragments, rip-up clasts the size of your palm. So highly energetic waves, rarely, or occasionally ripped away thick shale, dried out shale regions from, let's say, from a lagoon or from a big puddle or from a bay, a dried out bay. Were these just big storms or the high tide, or were these records of tsunamis? We are not quite sure yet. We'll find out. Third variety of conglomerates are tough conglomerates. You see the white clasts, they are tough, almost of a porcelaneous nature. They float, they are almost like pumice, they float. So you get strata that are inversely grained, inversely sorted, because the pumice clasts soak themselves full with water and settle pretty much simultaneously with the clay at the top of everything. We have quite a bit of laminated shale in the pro-delta environments. Some of the shale is rhythmically laminated, and we hope that we can use it for cyclostratigraphic analyses, or maybe to constrain even better the moon orbits and the days and lunar monthly lengths. Some of these shales, here we are clearly below wave base, right? Maybe in 20, 40, 50 meters water depth, are just absolutely beautiful. The dark segments are the shales, siliciclastic shales, chloride, illite, a bit of quartz maybe. The light colors represent tuffaceous sections, and of course the red colors represent ferruginous sections. And some of these jaspilites and minor BIFs become pretty thick. They are typically slumped, because I think because they represent a pro-delta environment, whether they are related to oxygen, either from photoferrotrophic bacteria active in the water column, or from periodic oxygen influx from the benthic microbial mats colonizing the shoreline. We do not know yet, but we will find out. The cores are usually silicified, and we ran the hyperspectral, Clement and Doe at the council ran the hyperspectral scanner over all of them. So the yellow, as you see here in the legend, represents quartz as the dominant mineral. Remember, most of this is cement, even though Moodies is quartz rich. There are also arkoses and litharenites and so on. But where you go into fault zones or shear zones, you then get chloride and siderite and other minerals. And of course, the ferruginous sections of our cores then show siderite associations. What happened to the core? As you learned, we cut them already the next day in Barberton and split them up into archive halves and work halves. The archive halves were shipped to the Donkerhoek National Repository here outside Pretoria, where they have been archived and scanned by hyperspectral. The working halves were shipped to the ICDP core repository at the federal German core repository outside Berlin in Spandau. So that took from end of July to about November. The usual steps. We were certainly glad to see them arrive, with ships sinking left and right, either in the Red Sea or in the Bay of Biscay. It would have been quite a bit of a loss. And there they arrived here in this beautiful facility, which used to be a Prussian cavalry barracks, and then after the war was used by the British occupying forces of Berlin as headquarters, and is now a core repository, and the Federal Survey resides in there. And there is the sampling workshop that we held in September, mid-September last year, attended by about 40, 45 people from all over the world, all these science team members that had participated in 2017 in the workshop. And many of them, of course, had quit since, and others had joined us. But we now have about 70 people in that group. And we just had a lot of fun, because weather allowed us to lay out in the open, under the open sky, all 503 of these core boxes, and then just take the sample lists I had provided all the participants with the cross-sections and the strat columns and the high-resolution photographs, so everyone pretty much knew where to go and what to sample. And then people lined up at one of the 3 core saws that we had operating for 3 days and asked that the half working core would be cut into quarter. One was then bagged and shipped to the home lab, and the other one went back to the working core. So we also generated, in the meantime, a massive data set of a reference geochemical data set, which is part of the overall data set and available to any BASE researcher. We did a number of techniques on figuring out the geochemistry. You see here from each meter, we took some pieces and we had them scanned in a core scanner. So we have a scanned XRF data point every meter of these 2,900. And then about every 2 to 5 to sometimes 10 meter, we took a piece out for fusion disk analysis, for grinding and powdering and other methods. So, and many of you are familiar with XRF and the various technologies. That, of course, because of the size of the task, was then done in a number of locations. And you see the core scans and the fusion disk samples, the Bruker Tornado, the MATLAB coding, quantitative powder, XRD, all done in different locations and all calibrated against each other and then put back together in one firm reference data set of 2,500 samples or so. That was a large task, which my geochemist colleagues are currently finalizing. Outlook. I'll show you 3 surprises. One, my fault. I was very surprised by the depth of weathering. Maybe because of me being principally a field geologist who likes to hop from outcrop to outcrop, I did not pay much attention to the grassland in between. But where we set up the rigs, of course, it was either in the forests or in the grassland. And we sometimes caught in one borehole through 80 meters of brownish, weathered, tuffaceous sandstone, completely de-cemented. And some of the cores were highly fractured, but many others were really good. Secondly, fortunately and luckily, to our joy, the banded iron formations and the jaspilites in the pro-delta facies were thicker and more beautiful than expected, so that all the interested parties got enough sample material. And thirdly, our education, outreach, publicity efforts paid off, and I think we had a long-lasting positive impact at a local and regional, perhaps even national level through all these outreach efforts, and that the drill sites here within the World Heritage Site actually already do and still will contribute to upgrading the World Heritage value of that site. To that end, we succeeded in converting, and that is largely due to Nick's efforts, and Michiel's and other people were involved here, to moving and upgrading this exhibition material into a new room, which was purposefully built here adjacent to the Barberton Museum or attached to the museum, and it's the BASE room, okay? It is a room dedicated to Archean geology and to the origin of life and to forward-looking and intellectually challenging and curiosity-based geology. And that will be dedicated and handed over next week to regional Mpumalanga government. Will be a small ceremony, and by now it's finished. I created some of the posters, and I'll quickly flick through here. Don't look at the details. Of course, there is the general introduction of what greenstone belts are and why here and so on. And we need to say something about the rock cycle to the left and about the strat column to the right here. But then I have been trying to put the reader or the audience more on a evocative mindset and to let the landscapes of the Archean rise again, both the atmospheres, the oceans, the volcanism, the depositional environments, the meteorite impacts, no photographs from meteorite impacts really, and of course the tides and the moon, okay? And all this is meant in order to to just challenge the viewer, the visitor to these rooms, or the reader of our publications, that geology, as we see it, there are other ways to see it in different ways, is more than looking at rocks. We use rocks the same way that an English major or an author is using ink and cellulose paper. We use it as a medium for the information. We are not interested in the printer's ink and in the cellulose. We are interested in the message. Okay, that's what these rocks should tell us. So, towards the end, what's next? Well, I finished writing the operational report. Scientific report has been submitted. There are now 46 registered research projects all over the world, and that are coordinated by me. That is, I'm just trying to avoid overlap. But we took 1,200 samples from 2,900 meters. That is, only every second meter has been sampled so far on average. And there are entire core trays that have not been touched. So if anyone, in particular petrographers, sedimentologists, stratigraphers, are interested, please talk to me. There's running room. Talking about running, there will be a next sampling workshop coming up next month, but it will be attended only by a few. And then I will hold for all these new PhD students a field workshop on the Moodies, showing them what the outcrop rocks next to their drill cores actually look like in July of this year. So what's left for me to do is first to profusely thank all our funders, both national and international. I'm highly grateful to CIMERA, of course, shown here, and all the funding and the organizational and administrative support that was extended through CIMERA and through UJ, and all the logistical support we received and so on. It could not have been done without you. Nick's actions and Nick's diligence freed me to concentrate and focus on the science and on running the day-to-day operations. And I was not involved in any of these financial and administrative issues, thanks to Nick's tireless work. And I would also like to thank, of course, GSSA for inviting me, and all the involved universities here for hosting me. Thank you very much. If towards the end now, at the second to last slide, to remember, it's about people. We had a wonderful team effort, and we succeeded in all our objectives. And we now have lots of running room to work with and to open new windows on the Paleoarchean Earth. And we hope to have to have made a bit of an impact on South African general community, at least at the local and regional level. If you asked yourself during this talk what this had to do with du Toit at all, I only can say two things. First, what an honor, to be in that line of all these illustrious geoscientists. And secondly, what I learned from du Toit, of course, then was everything starts with fieldwork and with diligent, maybe not fieldwork all the time, but with diligent and reliable and convincing observations that can then be turned into the explanation of processes and how world came to be this world that we are now living in. Thank you very much for your attention.
Christoph, thank you very much on behalf of everyone here. It's been a fantastic privilege to listen to you. The detail and the insights that you've gained already and will gain on this area are just inspirational. But I think the effort that you've gone to explore a part of South Africa's rich and intense geoheritage is really incredible. So thank you very much again. And let's open up the floor to questions for a few minutes before we enjoy some dinner and drinks. Any questions for Christoph? Gus?
It's clear that you've run a phenomenal program, obviously not single-handedly part of a big team. It occurs to me that your success in being able to achieve these project objectives under budget and maybe slightly over time could form the basis of a guideline for how other bodies could potentially approach similar projects that are regionally or locally important or internationally important. Is that something that the ICDP might be interested in? Or?
Yeah, maybe, maybe not. ICDP drilling projects are very diverse. One of the consequences of being funded by ICDP is, and running at least initially successful project is, you are then pulled onto the science advisory group. And you have to review all the others, the other proposals for 3 years. So you get to read the wide diversity, and they're all of excellent quality, typically, but very diverse. They drill magma chambers, and they drill the Colorado Plateau, they drill geothermal things, they drill ice ages. It's every single drill, every single ICDP program is very different and needs to be tailored to individual needs. Only in this case here, it seemed, and maybe only to me, opportune that I would bundle as much as I could stomach. Yeah, so this has occupied me for the last 6 or 7 years, and it's been great joy, and I'm still standing. And other ICDP projects are far better off to be managed by teams, yeah, that equally share the workload. I shared the workload too with Nick, who was almost as much engaged as I was. He came in because he saw that I needed help. I could not have done this as a foreigner, of course. So no, there are guidelines available, of course, already, but they have to be adjusted.
Can I just add to that? So the ICDP actually commended the outreach of this project. So in terms of the outreach component, that has been suggested that all the other ICDP projects look at how the outreach was conducted, the frequent weekly newsletters, the involvement of the community, and there have been several awards that the this BASE Moodies project have actually received. The Harvard Query, the Low-Felt Awards, and the ICDP itself. I have asked actually all the other project people to see particularly the outreach component.
Thank you, but we had to, yeah, because we were a bunch of foreigners claiming to be drilling for knowledge in a former gold province where we had successfully eliminated South African competition. And yeah, and the first few, there was one anecdote which is really funny. We had these open gates, yeah, big metal sliding gates, all the way pushed open. So we were wide open to the street and to anyone walking in. One day, 2 elder, swaggering Swazi gentlemen walked in, and they looked around, kind of like this and that, and who is in charge? Okay, I am, sir. For how long have you been in the country? Yeah. Well, I said, first time I came to Barberton was in 1989. Okay, so I had to establish credibility. Yeah, yeah, I came here in 2000. Well, good. So, what are you doing? And so I explained. And then he said, can you show me the gold library? And I said, well, sir, we are not the museum. Please, the museum is next door. And I sent them over. Yeah. But we were being checked. Yeah.